Hi everyone, in this video we're going to look at rates of change. So basically all rates of change is basically the gradient function. So if we're talking about a linear graph, and you can probably see if you've already looked at that purple box, let's just do a different color here. What we've got here is our gradient formula. So you'd remember back to year, I think it was year 8 or maybe year 9 when you started learning about the gradient. We would do y2 minus y1 over x2 minus x1. So basically that's all your average rate of change is. Okay, so if we had, say, a parabola, we know that the gradient is not the same at any point on that gradient, on that parabola. But if we wanted to look at the average rate of change between 2 points, it is a straight line. Okay, so that's why if we're looking at the average rate of change, we're looking at the gradient between 2 points. So if I just have a quick look at this Desmos graph that I've created, it's a linear graph. So that means the rate of change is the same. So let's say we were looking at the rate of eating donuts per minute. Okay, so we're eating donuts at 2 per minute. So after 1 minute, we've eaten 2. After 2 minutes, we've eaten 4. After 3 minutes, we've eaten 6, and so on. So our rate is the same. If it was a different graph, so let's say a parabola, just for comparison, let's see how easily I can put this up. All right, so your rate is different. So if I wanted to do the average rate of change between, say, the 0 minute, so the start, and at 2 minutes, you can see that would just be the gradient of that red line, which changes as that gradient changes. So if I wanted to, let's see if I can delete this without having to. Okay, so we'll put a slider in. So I'm just going to have a different gradient. So let's say I've started eating my donuts at t equals 0. So you can see the rate changes. So at the very beginning, the rate that I'm eating is quite slow, and then it gets faster and faster and faster. So it's increasing at a faster rate. All right, so just with rates of change though, and this relates to 10b, so I might just write 10b here. We're only looking at average rate of change, which is what you would use your gradient formula for, and instantaneous rate of change. Let's do that in green. And that's just your derivative at a point. So if we wanted to know how many, the rate I'm eating donuts at 10 minutes, you would find the derivative and let x equal 10. So we just find the derivative, substitute in a, your value of x that you want, and that'll give you your instantaneous rate of change. So those two things are what we do with rates of change. So average rate of change and instantaneous rate of change. Now, we will visit average rate of change again, okay, because when we do antidifferentiation, we're going to be looking at the average value. And the word average, just people stumble over it, like I just did then with what I was going to say. So we've got average rate of change and average value. Okay, so we're going to look at average rate of change now. We'll revisit just so you don't get confused between the two, because students always do. All right, let's move on because I don't want this to be too long a video. All right, so we can get our instantaneous rate of change just by finding the derivative and then just substituting in a value of x. So if your derivative is greater than 0, then as y is increasing as x increases. Okay, so it's a positive gradient. And if your gradient or your derivative is less than 0, then y is decreasing as x increases. So So it's a decreasing function. So if we had something like not a parabola, let's go back to Desmos and we'll change this one to a cubic. And change it to a better cubic. Now, I wanted to start this video so much that I didn't even bother thinking about what graphs I was going to do. All right, x minus 5. Is that going to give me something that's probably too high? Let's go back. Let's just do 1 so we can see it a little bit easier. All right, so just zooming into here. Oh, can I zoom in? Sorry, let me zoom in. Okay, so we'll ignore that red one for a sec. So you can see as on my graph, my cubic, it's the gradient's positive up until we get to this stationary point here at 0, 0, and then the gradient is negative, so it's decreasing. Yeah, let me touch you. There we go. And then it hits another stationary point, and then it's positive again. Okay, so we know that relationship between the derivative and its original function. Okay, so basically that's all we're doing. We're looking at the instantaneous rate of change or the average rate of change. Most of the questions in at 10B are actually just looking at the instantaneous rate of change. But if you have to do the average rate of change, just remember it's just y2 minus y1 over x2 minus x1. We've just got it written here in the purple box in function notation, so no different. All right, so let's do a question together. So the mass of a chunk of sandstone in m kilograms decays according to the rule. All right, let's highlight that. Very small highlighter, but anyway. M equals A times E to the power of negative 0.2 t, where t is in years. It's always important just to make sure that we know our units, because they might change. Probably not here, but we just got to be aware. All right, initially. Now, when I was looking, sorry, I'll stop reading that sentence for a sec. When I looked at this equation, what stood out for me was this A. All right, I knew that at some point I'm going to have to find that value of A. Okay, so we need to substitute in some values. So we've got one unknown, the A, so we need one bit of information. So that's where this initially part comes from. So initially, which is t equals 0, the mass of the sandstone is 5 kilos. So the m is equal to 5. So that means we're going to sub in the point 0, 5 to find A. All right, and that's what we're going to do in part A of question. State the value of A. All right, so let's substitute everything in. So here's my equation, m equals A. If you like, you can put a times in. Sometimes I like to add a times. All right, so there's our equation or our rule. Let's substitute in m equals 5. And then we've got e to the power of negative 0.2 times 0. So all of this, because we're multiplying by 0, is just going to be 0. So anything to the power of 0 is 1. So a is equal to 5. So our rule now becomes m equals 5e negative 0.2 t. Okay. Sometimes a question won't be broken up into steps like this one. So you will have to find A before you might have to do something else. So just be aware, sometimes questions aren't broken down for you when you do worded problems. Okay, so that was our answer for question A. I'm all over the place here. Let's go do B over here. So the mass after 5 years. So 5 years is T equals 5. So M, just writing our rule, 5e to the negative 0.2, and instead of t, we're going to put 5. Now, you could probably use your calculator It hasn't told us to simplify here, but I'm just thinking because we're dealing with E that we probably should, although this is going to be -1. So 0.2 times 5 is 1, so -1. And I'm guessing we'll probably have to do that on our calculator, which I haven't prepared. Let's see if I can easily get it up. Might have to pause. No, there we go, just a little bit slow. Okay, I really don't like you on that side. Can I move you? Okay. It's not cooperating though. Oh, there we go. All right, what are we doing? 5E. Oh, you're a little bit slow today, aren't you? I bet I press it and 2 E's will come up. There we go, told you. You're annoying. Start again. Oh. My computer doesn't like me today. There we go. So 1 point, we'll do it to 2 decimal places, even though it hasn't told us. So rounding, even though you've done it since early days, I'm going to teach you how to round. 8, 3, 9, we're only doing 2 decimal places. All right, so we do the cut after our 2 decimal places, then this is our deciding number, whether we round up or down. Are we going to round up to 1.84, and what are we in kilograms? All right, if you had to leave it as an exact value, you could. That would be the same as 5 over E. But it's a little bit weird writing it like that, so we're just going to leave it like that. This question was actually taken from a worksheet, which I think I have open. So, whoops, not that one. Let's just double check the answer, what the answers wanted. There we go. So it's rounded it to 2 decimal places. All right. Question C. I'm going to write that over here just to be all over the place. The average rate of change. So whenever you see rate of change, always remember you're referring to the gradient. Okay, so or your derivative. That'll help you not get confused with the average value, which comes later when we do anti-differentiation. All right, so we want the average rate of change. So let's highlight the average. Let's do that in blue because I think we did that in blue earlier. Average. So when we're looking at the average rate of change, and if you want to, you can just simplify it to that is just f of 5. So the 5th year, although we're not using f, are we? We're using m. Minus m of 0 over 5 minus 0, because we're doing it over the first 5 years. So we're going from t equals 0 to t equals 5. So we're going to substitute 5 in, which we did in the first part, so 1.84. Actually, always use the exact value. So 5e to the -1. And then our initial value was 5. Over 5 minus 0, which is 5. All right, if I was doing this by hand, I can take 5 out as a common factor. Not that I probably would, because we can, yeah, we don't need to do that. So, because we do need to have that decimal answer. So e to the -1. And just go across. So we're on the line, not as a power. All right, so -0.632. And we're going to round that to 2 decimal places. All right, not a hard one to round, 6.3. So that is our rate of change. So our rate of change is in kilograms per year. I was about to write second. I was like, what is it? What was the question about again? All right, so it's decreasing at a rate of 0.63 kilos per year. So that negative tells us it's decreasing. So if you had to kind of give a worded answer, or if it said what rate is it decreasing at, so it's decreasing at a rate of 0.63 kilos per year. Now, it's very important that you don't say it's decreasing at a rate of negative 0.63, because the negative sign is kind of already acknowledged with the word decreasing. It's kind of like if you lost weight. So if you went, I don't know, from 100 kilos to 90 kilos, you don't say I lost negative 10 kilos. You just say you lost 10 kilos. So just be careful of that. If you had a question that said what is the rate of decrease, you don't put the negative in. The rate of decrease is 0.63. That negative implies it's a decrease. Yeah. All right, so let's go back to question 2. Sorry, not 2. Oh my gosh, it is so late. Instantaneous rate of change. So we want to find the rate of change at t equals 2. So I'm really tired because my son is supposed to finish work at 7:30, and he's been asked to stay back until 10:30. So I'm a little bit delirious trying to stay up because it's well past my bedtime. Okay, you didn't need to know that. So rate of change at t equals 2. So we need to find the derivative. And this is important because up until now, we haven't really done too many worded problems. So we don't say dy dx, okay? Because y and x are not our variables in this question. M and t are. So we need to do dm dt. And basically the d stands for delta. So the change, and if you do chemistry, maybe even physics, or some sciences, I'm not really sure which other ones might do it. Delta just means a change. So we want the change in m over the change in t. So which is what rise over run is, the change in y over the change in x. All right, dy dx. So here, because we're using m and t as our variables in our question, our gradient function is dm dt. And if you're ever unsure which one's y and which one's x, just have a look at your equation. So what is in the place of where y usually is? M, okay? Or x is always your dependent, and t is often, in most cases, I would say 99% of the time, is your x, because x is something, sorry, I think I said dependent before. I meant independent. X is something you can't change. So t being time, you can't change. So that's mostly on your x-axis. Anyway, getting distracted. So what is our equation? Where are we? All right, so here's our equation here. So finding the derivative of that is not hard because it's just an exponential. Got a 5 out the front, that's fine. So we're just going to find the derivative of 5e to the power of negative 0.2t. So knowing our derivatives, we multiply the 5 by that coefficient of t, so negative 0.2. And then we've got e to the power of negative 0.2t. You could also do this on your calculator. So it's going to be negative e, because 5 times 0.2 is 1. If you find it too hard to deal with decimals, you can always change it to a fraction. So I might just do it over here. So 0.2 is 2/10. All right, it's in our tenths column, which is 1/5. So sometimes it's easier for people to deal with fractions. All right, so there's our derivative. We want it at t equals 2. So dm dt is equal to negative e, negative 0.2 times 2. If we were giving the exact value, that would be 0.4. Have you had a fraction as your power? That's also fine. Let's plug it in. we got negative 0.4. All right, and 0.670. I'll just round that now. Whoops, it was a negative. And kilograms per year. All right, so if you looked at the answers, all right, so you can see the units there as well. Kilograms per year, they've been rounded, they're not exact values, sometimes a bit unusual. The question usually states whether you should round or not, but yeah. So there's an example of average rate of change and instantaneous rate of change. So if you think of the word instant, it happens at one point in time. So for question D, it happened at 2 years, whereas average rate of change happened from 0 to 5 years, okay, over a period of 2 times. Okie dokie. Let's have a look at another question. Oh, sorry. A reservoir is being emptied and the quantity of water in V meters cubed remaining in the reservoir T days after it starts to empty is given by. All right, so here's our rule. We don't have to find anything there. I can see that's a little bit annoying that they've written the number 1000 as 10 to the power of 3, but that's okay. It's nothing that we can't deal with. All right, so question A, at what rate is the reservoir being emptied at time t? So if we're looking at what rate, that is your gradient. All right, so we need to find the gradient of this function. So I'm just going to rewrite that down here. So Vt, it's a bit annoying that that's in the way. I don't know how to move that. I'm just going to write over it. Ah! That's really what's going to happen when I do that. 10 to the power of 3, 90 minus t cubed. Now, obviously, we could do this on our calculator. So I'm going to show you once how to do it on the calculator because it's easy peasy Japanesey. But you should try to do as much as you can by hand, okay? Because something like this you can do by hand. All right, so interactive. Calculation, diff, for differentiation. All right, if you want to find it at a value, which we would if we were doing instantaneous rate of change, okay, stuff you've done before. It's just never been explained to you as instantaneous rate of change because we haven't done rate of change. But we just want to do differentiation. We only want to know the rate, okay, not the instantaneous rate, not the average rate. We just want to know the rate, okay? So that's our gradient function. All right, so 10 to the power of 3, or you can write 1000. 90, my 0 is right down the bottom, there we go, minus t. Now, you can put t in, I'm going to put x, just because I don't really want to navigate away and then do that, but if you put t in, just make sure you change that to a t. Especially if you ever define a function, you also need to make sure you're consistent with what variables you use. Now, this is also important. With your derivatives, my answer on my calculator has x. The question, there is no x, it's t. So you've got to be careful when you're transferring something from a calculator to your page to make sure that you're not writing x when it should be t. Okay, so let's write what the calculator has. All right, so 3000. Oh, 9. Ah, where are you going? It's not letting me write 90 minus t squared. All right, so notice how I've written the notation. So I've used function notation as opposed to Leibniz, that's how it's pronounced. If you were using the other notation, it would be dv dt. All right, so finding this by hand, you would use the chain rule. So we're going to let, even though I found it, I'm going to do it just quickly by hand. 90 minus t. I'm going to use u and y just because that's what I'm so used to. Y is equal to 1000, oops, very small, 1000, u to the power of 3. All right, so du dt is -1. and dy du is 3000 u. So dy dt is negative 3000 times u whoops, forgot to put the 2 there, 2 squared. And I just did a quick sneaky check on my calculator. I didn't write the negative before, but there should be a negative there. I wonder if you picked that up before. But we did the chain rule and I got it. So I was like, who's wrong? Well, I'm wrong both times. I just didn't copy it down from the calculator correctly. Okay, so you can see how I did it with the chain rule on the side on the right. Just make sure your final notation is consistent though. I wouldn't leave it as dy dt because there's no y there. So you can just make sure you write the final thing correctly. All right, part B. How long does it take to empty the reservoir? Whenever you see something that is empty, how much water is in there? 0. Okay, so V is equal to 0. This is not anything to do with the derivative. It's just a straight V equals 0. Vt is equal to 0. So let's just solve that. So 10 cubed, 90 minus t cubed equals 0. So divide both sides by the 10 to the power of 3, which is 1000. Then we could take the cubed root as well. So doing quite a few things in one go. So t is equal to 90, and we were measuring in seconds, days. Don't know why I always think seconds. All right, 90 days to empty this reservoir. 90 seconds would be very quick to empty a reservoir. All right, question C. What is the volume of water when the reservoir is t equals 0? So none of these, well, B and C, don't relate to the rate. Okay, so you've done these questions before when you've done, cubics. Okay, so we're just substituting in t equals 0. All right, so we've got 10 cubed times 90 cubed. Oh. All right, so you probably do this on the calculator. You can do 10 times 90 and then cube that, but let's just do that on the calculator. 10 cubed times, oh, actually that would be too hard to do because we know what 9 cubed is. Although I don't think you would have to do that without a calculator. Actually, that's not the answer I would have got. 7, 2. All right. Now, some of you might not have all those zeros on your calculator screen. So if you got an E, all right, just replace the E with the times 10 and then to the power. All right. So how many zeros do we actually have? 1, 2, 3, 4, 5, 6, so 729. All right, so you could write 7.29 times 10 to the power of 8. Don't know what your calculator might have. If you were doing this without a, actually you wouldn't do it without the calculator. 9 cubed is 729. Yeah, so that was too high. I was thinking of 3 cubed before, but 9 cubed. All right, so that is the initial volume. What was it in litres? No, it was in metres cubed. I didn't even have to scroll. I remember seeing that. Metres cubed. And it's the same as this. Either way is correct. Probably just sticking with all those zeros is better. Just make sure you count them all correctly. Where are we? D. After what time is the reservoir being emptied at 3 times 10 to the power of 5 meters cubed per day? Okay, so this time we are looking at a rate. So even though it doesn't say the word rate, this is a rate here. All right, meters cubed per day. So it's like speed. is distance over time, or what else is a rate? Can't think at the moment. So this is the volume per day, meters cubed per day. So we want our derivative to equal 3 times 10 to the power of 5. So we found the derivative before in question A, so I'm going to write that again. Just make it a little bit smaller so I can actually see what I'm doing. Where are we? There, keep it up. So here's our gradient again. All right, and we want that to equal, I can't remember what it was, 3 times 10 to the power of 5. Okay, so I would, what would I do? We can change this to be times 10 to the power of 3. That's probably why it would be good to leave it as 10 to the power of 3. Oops. All right, so just solving, I'm going to divide both sides by -3 times 10 to the power of 3, -3 times 10 to the power of 3. All right, so they cancel. So we're left with 90 minus t squared. And again, you could just do this on your calculator. All right, so 3 over -3 is -1 times 10 to the power of 2, which is just -100. Oh, I don't want a negative there. Where have I gone wrong? Is it saying decreasing? It's being emptied. There we go. All right, so quick check-in why I thought something's gone wrong here, because my next step would have been to get rid of this squared sign, which meant I would have to take the square root of a negative number, which can't do to get a real solution. So I knew, well, can't have a negative there. So because it's being emptied, I had to have a negative here, which gives me a positive. Fabulous. All right, I'll just get rid of that just so we can keep it. And then we can take the square root. So 90 minus t, square root of 100. Now remember, we should consider both solutions, both the negative and the positive. Oh, I'm running out of room. I don't want to go. Well, just go stop at D. Oh, sorry, I'll have to go on to the next page anyway. Okay, I just moved everything. So 90 minus t equals, so positive 10. And we're going to have 90 minus t equals -10. So just, what are we going to do? T is equal to 80, or t is equal to 100. What was the question again? After what time is the reservoir being emptied? Okay, so we know at a rate, after what time? So we know it's empty after 90 days. So we can't have 100 because it's already emptied. So, whoops. Might have to turn my emails off. Mrs. Valla's still working late. Okay, so no solution when t equals 100 because it's already emptied. It is empty at t equals 90. So t equals 80 is when our rate is, when it's being emptied at 3 times 10 to the power of 5 meters cubed per year. All right, so we'll just put a square around that. Years? Was it years? Days. Oh my gosh. It's like that's a long time. All right. Let's just change that. Days. There we go. It's a little bit better. All right. What's the next part? All right. So we're going to be sketching now. So I'm just going to do that on Desmos. You could do it on your calculator if you want to. Oh, let's do it on the calculator because you don't have Desmos on your exams. Okay, so let's go to the calculator. You're going to come? Thank you. All right, so our first one is 1,000. I'm just going to put 1,000. Oops. 1,090. Just use x to the power of 2. And we had the derivative in there, but it's not hard to type it in again. Whoops. She says that she can't even type a 0. 90 minus x. And I meant to put a cubed on that previous one, so let's change. Oops, not that one. The previous one should be a cubed. Okay, so just make sure. Come on, guys, cooperate. Just make sure they're in correctly. Alright. We might not see anything because we're working with quite a large volume. So you can press these buttons up the top. So I press this one here if you can see what my little thing is on. We don't see much. So I'm going to change my window using this button, you know. Alright, so my x minimum, I don't want to do 0. So I'm going to just do negative. You know what? Negative 3.65 is fine. Let's change the max to, what were we going to, 100? Oh, it doesn't want to work. Come on. I think it's tight as well. There we go. Scale doesn't really matter. Oh, now this is quite high. I don't know what we're going to see. What did we get as 729 million? Maybe that would be okay. All right. It's a bit hard to see. So the blue line, blue curve, is our reservoir being emptied. And then the red line is the rate that it's being emptied at. So you can see, it's a bit hard actually to see. Might zoom in. Oh, I can't zoom in. I want to just make a little box around here. It's not letting me. Didn't really want that. But anyway, let's just go looking at this red line. So see how it's, so the red line, we're graphing our red curve, we're graphing our derivative function. So it's below our x-axis because it's being emptied. Okay, so remember it's going down, and the rate that it's being emptied is increasing. All right, so you can see the gradient is getting higher. The gradient is increasing until it gets to 0 basically. And then you can see that blue, so the blue curve, you can't, once your reservoir is empty, we can't go below. So that's why we got 2 solutions for part E. All right, so there's your graphs. Maybe I'll show you what it looks like on the solutions. Well, you can see it's a little bit better here because I haven't graphed them on the same set of axes. So here we've got V against T. So you can see our initial volume when the reservoir was full, and then it's being emptied, and at 90 days it's empty. And then F is our gradient, so the rate that it's being emptied. So you can see at the very start it's being emptied at quite a high rate, and it's a bit hard to understand because we are negative, but remember when something's being emptied it's negative. And you can actually see, if you thought about going down this V versus T graph as a, if it was a slide, it's very steep at the beginning and then it kind of flattens out like a slide usually is. Okay, so that's why we're right down here. And then it gets closer and closer to 0. All right, now I actually had other things to talk about here. So let me just quickly see if I did a question. Okay, I might stop this one and just do it in 2 parts because I think I need a drink of water. And you can, finish there. That's 10B. This second part is actually 10F. So even though I want to do them together because they're related, but if you want to come back to it later, it's fine. Okay, bye.